Burn like a pro.
Have you ever wondered how you can feel the warmth from a campfire even when you're sitting pretty far away? Or why your coffee goes from piping hot to lukewarm just sitting on your desk? Well, it's all thanks to this invisible force, a constant back and forth of energy that shapes our world. Today, we're going to decode that thermal blueprint. Let's get right into it.
And the best place to start is with a real head-scratcher. We all learned that heat needs something to travel through, right? A solid, a liquid, a gas. But think about it. Between us and the sun, there's about 93 million miles of cold, empty space, a vacuum. So, how on earth does the sun's heat make it all the way to us? The answer, in one word, is radiation. Now, unlike its cousins, conduction and convection, which need to physically pass energy from one particle to another, radiation is totally different. It travels as electromagnetic waves. They don't need any medium at all. They just zip through the vacuum at the speed of light, solving what we can call the medium paradox and, making all life on Earth possible. No big deal.
All right, so now that we know what radiation is, let's pop the hood and look at the rules of the road. This is the fundamental blueprint for how pretty much every object in the universe deals with heat energy. Okay, rule number 1 is simple, but it's a big one. Basically, everything is in on the action. If an object has any heat whatsoever, and that means anything above the coldest possible temperature, absolute zero, it is constantly, simultaneously, both sending out and taking in radiation. It's this continuous, invisible dance of energy that's happening literally everywhere all the time.
And this is crucial, not all surfaces dance the same way. The second rule is all about what the surface itself looks and feels like. You can basically split them into two teams. On one side, you have dark, dull, and rough surfaces. These guys are champions at both absorbing and emitting radiation. They're just better at soaking up that wave energy. On the other team, you've got light-colored, shiny, and smooth surfaces. They are terrible absorbers and emitters, but they are fantastic reflectors. This split is key to everything that follows.
And we can prove this with a really simple experiment, a kind of thermal race. First, you stick 2 flasks, one black and one silver, out in the sun. The black one, of course, gets hotter, faster. It's a better absorber. No surprises there. But here's the cool part. You then take them both into a dark, cool room. And guess what? That same black flask now cools down faster because it's also a better emitter. It proves the principle perfectly. If you're good at absorbing heat, you're also good at getting rid of it. So, knowing the rules is one thing, but how do you control the rate? How do you speed this energy transfer up or slow it way down? Well, let's look at the variables we can actually adjust, the thermal dials we can tune. It really boils down to 3 main controls on our diagnostic dashboard here. First up is surface color and texture, which we just covered. The second dial is surface temperature. Pretty straightforward. The hotter something is compared to its surroundings, the faster it's going to radiate that heat away. And third, and this one's a biggie, surface area. The more surface you have exposed, the higher the rate of radiation. Let's really focus on surface area for a second because it can be a little counterintuitive. Take a look at these 2 objects, A and B. Now, believe it or not, they both have the exact same volume. They're made of the same amount of stuff. But just look at that difference in their total surface area. Object A is a nice compact cube. Object B is all stretched out and thin. And here's why that matters so much. Because object B has a surface area that's almost 3 times larger, it has way more real estate for emitting and absorbing radiation. So even if they both start with the exact same amount of heat inside, object B is going to cool down or heat up way, way faster than object A. It's all about giving those energy waves more room to play. And this is where the physics gets really powerful. See, once you understand this blueprint, you can start to engineer solutions to control heat flow. Let's check out how we apply these rules to solve some very real-world problems. Take a simple space blanket. This thing is a genius piece of surface engineering. That shiny, smooth surface is doing 2 jobs at once. When it's facing in, it's a poor emitter, so it reflects your own body heat right back at you, keeping you toasty. But if you're near a fire, that same surface facing out is a poor absorber, so it reflects that dangerous external heat away. It's one surface playing both offense and defense. Now, for a true masterclass in fighting heat loss, let's look at the vacuum flask, or, a thermos. This exploded view shows you just how much clever design is packed in there. Every single part has one job, to defeat a specific type of heat transfer, whether it's conduction, convection, or radiation. So let's break this down with some builder logic. The vacuum between the walls, that stops conduction and convection dead in their tracks. The stopper up top,
That handles convection too. But what about radiation? Well, that's the secret mission of those silvery glass walls. Just like our space blanket, they're shiny and smooth. That surface acts like a mirror for infrared radiation, bouncing the heat from your coffee right back into the coffee, stopping it from escaping. It's a perfect real-world use of our second rule.
Okay, so we've seen how these rules work for coffee flasks and emergency blankets. But what happens if you scale this whole concept up, like to the size of an entire planet? Well, it turns out the exact same physics is at play.
To get our heads around this, just think about a simple greenhouse. Short wavelength light from the sun passes right through the glass, no problem. The ground inside soaks it up and gets warm. But here's the trick. The warm ground then radiates that energy back out, but as a longer wavelength infrared radiation. And that long wave stuff can't get back through the glass. It's trapped. The heat literally gets stuck inside. And our planet's atmosphere works in a very similar way. Just like that greenhouse glass, the sun's energy comes in, warms up the Earth's surface, and then gets radiated back out as that longer wave infrared heat. Greenhouse gases in the atmosphere then act like the glass, absorbing and trapping a lot of that outgoing heat. The source material notes that as human activities add more of these gases, this trapping effect gets stronger, which drives up global temperatures. It's the same wavelength trap, just on a massive planetary scale. And this brings us to a really fascinating point. The very same principles of infrared radiation can be used to achieve two totally opposite results. On the one hand, you can set up barriers to trap those emissions and overheat a system, like our planet. But on the other hand, you can engineer a shiny surface to reflect those exact same emissions and perfectly isolate a system, like keeping a person warm in a space blanket. So you see, it all comes back to these same fundamental rules: absorption, emission, and reflection. The physics is clear. We have the thermal blueprint. We understand how energy moves through our universe. The only question left is, how are we going to choose to build with it?